All right, hi there. We're going to talk about redox reactions, and let me just get right started into it. I wouldn't take notes on this slide, I just want to kind of intro what they're all about. So if we take a look at this reaction, on the top part I've got the Lewis dot structures, and on the bottom part I've just got the balanced equation. They're the same equation. So here, when I'm looking at hydrogens, the two hydrogens together are sharing electrons, these two right in the middle, and they're sharing them equally. One hydrogen doesn't love electrons any more than another hydrogen. Here's oxygens. They're sharing these electrons in the middle, and they're sharing them equally. One oxygen doesn't love electrons any more than another oxygen. But when we look at this one over here, we've got water. And in water, they don't share electrons equally because oxygen loves electrons more than hydrogen does. It's more electronegative, which means that the electrons tend to be around the oxygen more often. If they're around the oxygen more often, they've kind of gained electrons in a way. And the hydrogen, they don't have the electrons around them anymore. Before, over here, they were sharing them equally, but now they don't. So now in that sense, they've kind of lost electrons. This type of give and take of electrons is what a redox reaction is. So let me show you another one, a little bit tougher. So you got Lewis dot structures again, and we'll have to look at where are they sharing electrons equally and unequally, and how are the electrons on the other side, but that gets kind of annoying, and the chemists, they're not a big fan of that either. So we want to find a shortcut way to do things. So that's what I'm going to start with today. To look at the Lewis dot structures and draw those every time, to look at electronegativity and then look at it in 3D, the VSEPR structure, it gets a little complex. So we've come up with a system that allows us to do things in a lot shorter of a time period and track electrons where they go, where they leave, and where they come to. So that's what this is about. Just like you have to learn how to read, whoop, that got big. Just like when you learn how to read, you've got to learn your ABCs first. Well, this is that same idea. Why is that doing that? Let me pause it. There we go, I fixed it. So just like when you learn how to read, you have to learn the ABCs. And at first you're like, why do I have to learn the ABCs? But then you learn words, and then you're like, why do I have to know words? Then you learn sentences. Same idea here, there's step by step. So our first ABC part is oxidation numbers. Oxidation numbers are these plus and minus numbers that we as humans have decided to assign to these electrons. And because we have this system, we can track where electrons go. So they're an electron tracking system. So that's what we're going to do first, is assign oxidation numbers. My pen is not working. This is kind of not going to be as best to writing. I got to use a mouse, but I think we can get through it. Okay, so when we're assigning oxidation numbers, I got this flow chart. Now, in your textbook, there's a whole list of like 7 or 9 rules. So if you don't like the flow chart, the textbook will have a list of rules and you can memorize those ones and maybe it's more helpful. I find that most students really like this method though, because the less rules you have to memorize, the better. So if you think about all the compounds, we really have 3 different types. The first type is one type of neutral element. If we got one type of neutral element, the oxidation number is always 0. So in other words, if we got magnesium right here, it's just one type of element, it's neutral because it has no charge, its oxidation number is 0. That means it has the right amount of electrons. They're not sharing them unequally with anybody. Potassium by himself, oxidation number 0. Here's oxygen. It's one type of element, oxygen. There happens to be 2 of them, but that's fine. But their oxidation number is 0. That's like when we drew at the very beginning. We looked at O2. And we saw that they're sharing electrons equally. So each oxygen, it's not that one oxygen has electrons and the other one doesn't. It's that they're sharing them equally. So we call their oxidation number 0. Okay, now we're going to move onward to ionic. Yeah. Ionic compounds, as a reminder, is when you take a metal and we add to it a non-metal. So metal is on the left side of the periodic table and non-metal is on the right side of the periodic table. So I always look for a metal first, like K, that's a metal. And then what we're going to do is the oxidation number is the same as the ion charge. So probably on your periodic table at the very top, you have like +1 and +2. And then over on the other side, on the way far right side, it's a 0 and then a -1, a -2, -3. That's what we're thinking about here. So like at K, if he's going to have an ion charge, he'll be called a +1 charge. His oxidation state is also +1. Oxygen, if he has an ion charge, he's called -2. His oxidation state is also a -2. And if we look at how this works, since there are 2 Ks, +1 times 2, that's a total of a +2 part right there. My oxygen is a -2, and so altogether they add up to a 0, which is good because the whole molecule, or in this case an ionic compound, has no charge. Let's go to aluminum bromide. You look on your periodic table, you'll see that aluminum is a 3+. He's 3 rows over in the metal section. Bromine is on the far right, but 2 over. So the far right column is 0, then a -1. So bromine is a -1. If we add them all up, 3 bromines make a -3 total. And aluminum's a +3. So yep, you guessed it, it adds up all to 0. Perfect. I do always like to double check it because then you know for sure you didn't make a mistake. All right, taking a look at magnesium. He's 2 rows over. He's a +2, ion charge and oxidation state. Nitrogen's a -3. And if we take a look at what we've got there, the -3 times the 2, that's a -6. The 3 times the +2, that's a +6. And again, it adds up to 0. The important part here is not the stuff I've written on the bottom. That's kind of like your math work to check yourself. The important numbers are the top numbers. That's where a question would be like, what's the oxidation state of magnesium? You'd say +2. It's not that it's +6 because you need to know for each individual atom. +2. All right. And last but not least, the covalent or molecular compounds. That's when you're going to take a nonmetal plus a nonmetal or however many nonmetals you have, but it's all nonmetals. So I'm going to chop it off right here because everybody on this left side is all nonmetals. So in a covalent compound, and actually 99.5% of all the compounds, H is always a +1, O is always a -2, and the rest you kind of figure out from there. And that rule really does tend to work out. I don't actually have an exception I've ever run into where it fails. So let's go over here. H is a +1, O is a -2. Then I'm going to figure out what I got. Well, I have 4 O's. 2 times 4 is a -8. I've got 1 H, that's a +1. They all have to add up to 0, so the only way to make that happen is if my I happens to be a +7. And they all add up to 0 then. Take a look at this one. O is a -2, H is a +1. Again, they have to all add up to 0. My O here is a -6. I've got my H is a +1. So that means my iodine in this case has to be a +5. Hoping you're getting the pattern here. Again, O is a -2. H is a +1. So then they all have to add up to 0. The only way that could happen is if my I is a +1 also. And last but not least, it's one of my favorite. It's the high. H is the +1. This is actually called hydroiodic acid. And I is a -1 in order to make the H work out and add up to 0. So one thing to notice with all of these is that you can see my I was a -1 here, +1 here, +5 here, and then a +7 here. So they can change as depending on who they're hooked up with, and that's because sometimes they share electrons equally, how the Lewis dot structure is set up, all that beginning stuff. But we don't need to draw the Lewis structures to figure that out. We can look at these numbers here. All right, look at the last guy here. This is just a random one. When I look at it, I've got to decide what column I'm in. Definitely not one type of element. So I'm just trying to decide if it's ionic or covalent. I do see Na here, and he's a metal. So I'm going to call him +1 because I'm in the ionic area. O is a -2, whether you're in the covalent lane or the ionic lane, make it a -2. There's very few exceptions. I don't think your textbook goes into it at all. I wouldn't go into it unless we were in AP, so you don't have to worry about it. And then I'm going to add them up. My oxygen here is a -8. The 2 sodiums there makes it a +2. And so the only way to make that work is if my sulfur happens to be a +6. Okay. These are the ones I would say you should try, and then I'll show you my answers there, okay? So give that a try, and the next slide will be the answers. All right, here are the answers. Push pause so that you can actually check them over, because I'm going to keep rolling. My pen's working again. It's good. We played bamboozle. We don't have time for that right now. But then we moved on to, okay, now that we know what oxidation numbers are, let's decide who lost and who gained electrons. This brings us back to that first problem. There is where we learned that you gain electrons and you lose electrons. When you're gaining electrons, it's called reduction. And if you lose electrons, that's called oxidation. Just 2 vocab terms to know. Here's how I remember it. This is this cute little guy. His name is Leo, and he goes grr, because lose electrons oxidized, gain electrons reduced. Little mnemonic device. Or you could use this one, oil rig. Oxidized is lose, reduction is gain. I would use one of those. I still use Leo goes grr in my head. I think it all the time. I think your textbook does talk about these too. So hopefully one of those will work for you to help you remember who's oxidized and who's reduced. All right, so let's take a look at this one. I've got the oxidation states on the top. So I want to identify who changed from the left to the right. Manganese here is a +4. And if I look at the other side, he's a +2. He has changed. The other thing that's changed is the -1 of fluorine is now a 0. That's another change. The only way you can go from a +4 to a +2 is if you lose negative things. Wait a minute here. I am wrong. Back up. Back up the truck. Okay, try again. +4 to +2. The only way you can be going to become +2 is if you gain something that's negative. You gain electrons in this case. The only way to go from +4 to +2 is if you gain 2 negative things. In this case, we gained 2 negative electrons. So if I gain electrons, that would be called reduced. I would say that manganese is the thing that's reduced. On the other part right here, I've got a -1. I'm going to a 0. The only way that can happen is if you lose electrons. If you lose that 1 negative electron, you'll become a 0. Losing electrons means you're oxidized. So I would say that chlorine is the thing that's oxidized. There we go. Taking a look at this guy right here, why don't you pause it and put in oxidation numbers, and then try to decide who's oxidized and who's reduced. Give it a pause, because I'm going to go over the answers. Here's my oxidation numbers. And then here's how I decide who's oxidized and who's reduced. If you lose electrons, you're oxidized. You gain electrons, you're reduced. Taking a look at this problem right here, I put in oxidation numbers, and if you carefully look at them, take a pause, try to find who's changing from the left to the right. I'm short on time, so I can't wait too long. Calcium goes from +2 to a +2. That didn't change. Carbon, -1 to -1. That didn't change. H, +1, +1. That didn't change. O, -2, -2. That didn't change. There were no change in the oxidation states. This is not a redox reaction. Nobody lost electrons, nobody gained electrons. I don't believe your textbook goes into that, but I want you to be aware of it is possible not to be a redox reaction. Completely possible. This is not a redox reaction. All right, these were 2 practice problems that I had in class that we did, and you'll see the answers. I don't know what I said down below. So if you want to pause it and give those a go, that's a good way to go. Here are the answers on there. You can slide through there. There's one error. This is not a +4. This is a +5. I fixed it right here. We played bamboozle again. We gave this one a go. And then we did a lab. I will send you the picture of the lab. Wait, I can find it. All right, here's the lab. It's posted so you can check out the directions, but we basically mixed these solids, like this is magnesium solid right here, and we put in it this solution, zinc chloride and copper chloride, and a reaction happened. So if I zoom in here, you'll see that this really didn't do anything. That's a paperclip. Zinc is what a paperclip's made of. It looks like a paperclip and nothing's happening. Same for these pennies. Nothing's really happening. But if we go to the top here, do you see how there's little bubbles? This one is a blue solution that I put in, but you can see there's a bunch of like scraps of stuff that shouldn't really be there. That was made. And then this one, a paperclip does not look black. It produced this blackishness. So the ones that made a reaction were these top ones, and the ones that didn't make a reaction were these bottom ones. And then what we did is went through in the lab why that would be. So it might be really helpful without just listening to what I have to say here to go back and actually do the lab that goes with it. And it kind of guides you into what's really happening. So that would be an option. Totally, you do not have to do it. We did it all in class, so I'm not collecting it all. We completed it all and we talked about it. So this is what I'm going to talk about it. What we found, if we looked back in there, is that the magnesium solid, this one reacted and this one reacted. In the zinc, only this one reacted. In the copper, none of them reacted. So the most reactive metal was magnesium, then zinc, then copper. Magnesium, least reactive, copper. And then we wrote some reactions, and we saw that when you put magnesium solid into copper chloride, a reaction happened. This one happened. But it didn't happen if I did it backwards. Like the copper solids, they never made a reaction happen. So that didn't work. So then we related it to electronegativity. And electronegativity is the idea of how much you love electrons. A really high electronegativity means you really love electrons. If I look at the chart, these up here have a really low electronegativity. These down here have a really high electronegativity, which means copper loves electrons, and magnesium and zinc, they hate them. So when I try to explain how this all works, we looked at it. Magnesium here, he lost electrons. That's good because he hates them. Copper, he gained electrons. That's good because he loves them. So a redox reaction will happen when everybody gets to do what they want to do. Magnesium wants to lose electrons. Copper wants to gain them. This reaction will happen. The reverse will not, because that makes everyone do what they don't want to do. So the rule that I'm going to end you with is as long as the solid is above the aqueous, the reaction will happen. My